So good morning to everyone. Come fast. So good morning. Fast, fast, fast. Okay, good morning, good morning. So as usual, before starting with today's concept, we will have a discussion about whatever we have discussed in the last class. Fine? So now, when it comes to last class, good morning Appa, good morning. Okay? So when it comes to last class, we have discussed about what we had discussed. We have discussed about the chemical properties, right? So that's what we have discussed about the chemical properties related to group 15 elements. So we have discussed about chemical properties related to group 15 elements. Okay, fine. Once again I am back. There was a call. So now with respect to chemical properties, we have discussed about first one is hydrides. We have discussed about hydrides. So that's where ammonia will be having higher basicity compared to phosphine, which will be having higher basicity compared to arsine, which will be having higher basic property compared to antimony. Then we have discussed about bismuthine, right? So stibine or antimony or sign. So that's where we have the basicity. That is with respect to basicity. Decreasing order of that basicity, right? Now when it comes to reducing property, it will be reverse, where BiH3 will be higher property compared to stibine, then compared to arsine, which will be more compared to phosphine, and the last one will be ammonia, right? So that's what we have discussed. So what do you mean by basicity? Basicity is nothing but how many H plus it can neutralize. So in that way ammonia is more efficient. And with respect to donation or formation of hydrogen, so bismuthine is going to dominate. That's where we have the basicity and reducing property. That's what we have discussed in the chemical properties. Fine. So now, why bismuthine is having higher reducing property? Due to weaker bond strength present. Therefore, bismuthine will be having higher reducing property. Fine. So now, once after hydrides, we have discussed about oxides, right? So we have discussed about oxide. Now, when it comes to group 15 element, they will form E2O3 and E2O5 type of oxide. Now, when I am talking about oxides, as we have discussed, so nitrogen and phosphorus oxides, they are acidic oxides, and when it comes to arsenic and antimony, their oxides, they will be amphoteric. What do you mean by amphoteric? Where they can behave as both acid and base. And the last one, that is oxides of bismuth, it will be basic in nature. These things you should remember. So group 15 elements, they will form E2O3 and E2O5 type of oxide, no doubt. But in that case, nitrogen and phosphorus oxides, they are acidic, and arsenic and antimony, they are amphoteric, and bismuth oxide will be basic oxides, right? So non-metals, and this one metalloids, and this is a metal. So that is with respect to oxides. We have to remember even this one. Fine. Then we have discussed about halides. Then we have discussed about the halides. Now when I am talking about halides, as we know, nitrogen cannot form EX5 type of halides, because when it comes to group 15, they can form EX3 and EX5 type of halides. They can form EX3 and EX5 type of halides. But this one, nitrogen will not form. Nitrogen is not going to form EX5 type of halides. What is the reason? That is due to absence of D subshell in the outermost shell, right? So that's where we have the nitrogen, one of the anomalous property of the nitrogen. Now with respect to trihalides also, NF3 is the one which is quite stable. Among the trihalides of nitrogen, NF3 is the one which is quite stable. Other trihalides of nitrogen are quite unstable. Fine. So that's what we have discussed in the last class. Then with respect to metals, they will form respective. For example, nitrogen will form nitrites. Right? Now, we have also discussed about the nitrogen, elemental form of nitrogen, that is N2. Now, commercial preparation will be from atmospheric gas, right, or from atmosphere, where first one will be liquefaction, then based on the difference in their boiling point, that is fractional distillation, they will be separated. Fine. So that is commercial preparation. Then the laboratory preparation will be by treating ammonium chloride with sodium nitrite, right? So where one of the product will be nitrogen. This is laboratory level preparation or small scale preparation. Same way, thermal decomposition of ammonium dichromate, NH4 twice, Cr2O7. Thermal decomposition of this one can also lead to the formation of nitrogen. So these two are example for small scale preparation. Now purest form of nitrogen or pure form of nitrogen can be obtained by decomposition of nitrites, by the azides, by the decomposition of azides. So what are azides? N3 minus. Azide is nothing but N3 minus. So that's where we have azide. And we have discussed about barium azide. So we have discussed about the barium azide, where Ba plus 2. It will be plus 2. And here it is minus 1. Therefore, BaN3 twice. So when I will heat barium azide, they will get decomposed as nitrogen. So this is one of the method where we can get pure form of nitrogen compared to others. We are going to get the pure form of the nitrogen. Now very important point here is nitrogen at room temperature, it will be less reactive or non-reactive, right? So nitrogen at room temperature, it will be non-reactive, or we can tell it is inert. But please remember, I am talking about at room temperature. I am talking about at room temperature. Yes, Ravikant, it was barium azide. Fine. Now when it comes to nitrogen, at room temperature they are inert. So now the question can be, why nitrogen are least reactive or inert at room temperature? What is the reason? So the answer will be due to the presence of triple covalent bond. due to the presence of triple covalent bond. So therefore, nitrogen at room temperature will be inert or very less reactive. All of you have understood? Fine. But now we will come to that is chemical properties of nitrogen. But when I am talking about the same nitrogen molecule, if I treat with the metals, if I heat with metals, whatever nitrogen is there, if I heat them in the presence of the metals like lithium, now the product will be, as we have discussed in chemical properties of group 15 element. We have discussed about nitrides, right? All of you will agree, calcium nitride. We took the example of calcium nitride. Any one of you can recollect and tell me what was the oxidation state of nitrogen in that compound? In calcium nitride, if you recollect, what was the oxidation state of nitrogen in nitride? Anyway, so here it's going to form lithium nitride. I am not going to write the molecular formula, but if you recollect in last class, you people have counted and I have told what was the oxidation state. So Ravikant, you are wrong. It's not 2. As Mayank is telling, it should be -3. Remember this. So nitride is that compound where nitrogen will be with -3 oxidation state. Nitrogen will be with -3 oxidation state. Now here lithium will be +1, right? So one lithium can be +1 because group 1 element. So in that case, lithium nitride, it will be LIN. Fine, I will write LIN. But that is not correct, right? Lithium is +1, nitrogen will be -3. So therefore, Li3N. Right? So that's where we have the lithium nitride. So what are nitride? So these are the compounds -3. Yes, Ravikant, it will be Li3 is balanced? No. So here it is 2. So I will multiply it by 2. So here it should be 6. Here it should be 6. So what I mean to tell you is, one of the chemical property of nitrogen is when they heat with in the presence of metals, they will form respective metal nitrides. They will form respective metal nitrides. All of you have understood? They will form respective metal nitrides. Okay? Now, same way, whenever nitrogen is heated, not at room temperature, please remember, when you are heating it, then only I am telling. When nitrogen is heated with oxygen, when nitrogen is heated with oxygen, now they are going to form nitric oxide. Now they are going to form nitric oxide, NO. Nitric oxide, NO. Fine. So that's where we have some of the chemical properties of the nitrogen. All of you have understood? So when nitrogen heated with metal, here I have taken the example of lithium. Now they will form lithium nitride. So what are nitrides? These are the compound where nitrogen will have -3 oxidation state. So they will form nitric oxide, NO. Nitric oxide. Fine. So now another important property I have not mentioned. So that one we are going to discuss as one of the very, very important concept, that is commercial preparation of ammonia. There is nothing but commercial preparation of ammonia. We are going to discuss that chemical property of nitrogen under this title. Commercial preparation of ammonia. Many times they have asked, and it will be asked for 3 to 4 marks. Fine. So therefore, very, very, very important. Okay, so you can expect any one of the three process, because total we have three in P block. One is this one. Same way we have commercial preparation of nitric acid and commercial preparation of sulfuric acid. So among these three, 100% question, right? So that's where we have the commercial preparation of ammonia. So commercial preparation of ammonia will be called as Haber's process. It is the name of the person, Fritz Haber, who designed the process or who designed the reaction condition so that commercial preparation of ammonia can be done. First thing here is why we want ammonia. What is the requirement of ammonia? Why we have to prepare ammonia? That is quite natural question, right? Now when you are talking about ammonia in your laboratory, chemistry lab, you can see ammonia solution bottle is there, right? So that's where ammonia is required for the preparation of ammonia solution for the chemical industry or in the chemical laboratory. It is required, very much required chemical. Fine. So along with that, ammonia is having huge application in fertilizer industry. That is, ammonia can be used for the synthesis of urea, one of the important fertilizer. So like this, ammonia is having lots of application. So therefore, we have to prepare, or there is a huge requirement or demand for the ammonia. So that's where we have the large scale preparation of ammonia or commercial scale, one and all same, large scale or commercial scale. So that's where it is called as Haber's process. Now, if I write the reaction, that will be another chemical property of nitrogen. If I write the reaction, that will be another chemical property of nitrogen. For example, we have nitrogen. Anyway, this one, to some extent, we have discussed in surface chemistry. We have discussed this one in surface chemistry. 1 minute. Okay. So this one, reaction, Haber's process, we have discussed in the surface chemistry. Can anyone tell me under which concept we have discussed Haber's process in surface chemistry? Anyone? See, all of you are thinking. That means not reading. Okay, fine. Sir, surface chemistry above ಮಾಡಿದ್ದು sir. It is cheating. After that we did biomolecules, chemistry in everyday life, polymers. Then how we can remember surface chemistry? Yes, I agree. But by chance, anyone, Lee-Chandler's principle? No. Lee-Chandler's principle is in chemical equilibrium, first year. Yes, Kritik, very good. Catalyst mechanism, which catalyst? Heterogeneous catalyst. If you recollect, I took this example and I told we are going to discuss same thing in P block, right? So that's where while talking about mechanism of action of heterogeneous catalyst, right? So that's what we have discussed in the surface chemistry. So that mechanism I am not going to discuss here. Here we are going to focus on condition, reaction condition. So in that way we have, they ask, explain the steps involved in the commercial preparation of ammonia. If that is the question, then first sentence should be, it is called as Haber's process. That should be the first sentence. Next, you should give the reaction. You should give the balanced chemical equation. So that's where we have the ammonia, right? So that's where we have the ammonia. It is not a balanced equation. Here 2 nitrogen, here it is only 1. So 3 2 is 6, I will make it as 3. Now it is a balanced equation. Fine? So that's where we have the reaction. Now if you observe it carefully, in reality, this reaction will be a reversible. Don't write this reversible sign. To make you understand, I am writing. In reality, it will be a reversible reaction. All of you can see the board. In reality, it will be a reversible reaction, right? For a chemical study, if it is a reversible reaction, that is fine. But we are not talking about chemical property or chemical study. We are dealing with the commercial preparation. So what do you mean by commercial? That means I have to have the profit. So that way, I cannot go with the reversible process where ammonia will be produced and once again it will be dissociated into nitrogen and hydrogen. No, it's not acceptable. So what we have to do is, since I require ammonia, we have to make this reaction irreversible. We have to make this reaction irreversible. To make the reaction irreversible, we have to provide the condition. Yes, Sarchit, on large scale. So therefore, we have to make reaction irreversible. So to make irreversible, we have to provide some of the conditions where we can make this reaction irreversible. So which is that condition? You can write on the arrow or we can write it as reaction condition. We can write it as reaction condition with separate title, right? So now one is they will be using pressure. Pressure will be somewhere around 20 megapascal, very high pressure, unimaginable amount of pressure, 20 megapascal, right? So now 20 megapascal means if I want to convert it into pascal, mega I think it is 10 to the power of 6. So in that case it will be 2, 3, 4, 5, 6. That many pascal, oh my god, huge amount. We cannot imagine such a high amount it is. So many people, why I am writing this one? Because many people they will write 20 pascal, which is absolutely wrong. It's not 20 pascal, it is 20 megapascal. Fine? So that if you want to write it in pascal, so many this one. And you cannot imagine in atmospheric pressure, ATM. It will be very huge value, right? Because 1 pascal is equal to nearly 1 lakh ATM or 1 lakh bar pressure. So you cannot imagine. So we'll go with the pascal only, which is the SI unit. So that's where we have the pressure as 20 megapascal. Now, temperature. I am talking about reaction condition and you have to write all these things. If you don't write, you are going to lose the marks. So temperature, it will be somewhere around 700 Kelvin. Temperature will be somewhere around 700 Kelvin. Then catalyst, all of you know. Catalyst already we have discussed. It is a heterogeneous catalyst, that is iron oxide powder. So it is a heterogeneous catalyst. Heterogeneous catalyst, which is that one? That is nothing but iron oxide powder. Right? So that's where, or you can simply write it as iron oxide, no problem. So catalyst is a heterogeneous catalyst, that is iron oxide. Fine. Now we are going to use the promoters, catalytic promoters, which is going to enhance the, what do you mean by catalytic promoters? So these are the reagents or chemical which will enhance the catalytic activity of a catalyst. They are called as catalytic promoters. So in that case, catalytic promoters will be alumina, that is aluminium oxide, alumina or aluminium oxide, or even we can use K2O, that is potassium superoxide. K2O, anything is fine. Potassium superoxide. Something, Ravikant, 210 to the power of 5. Yes, that's what. Okay. So that's why we have the, if you want to convert it into Pascal, because mega means it should be 10 to the power of 6. It should be 10 to the power of 6. So therefore 6 is there, already 20 is there, so okay, fine. So that's where we have the 20 megapascal. Fine. So that's where we have the catalytic promoters. Everything should be there. Fine. And if you mention heterogeneous catalyst, it will be much more advantageous. If you write iron oxide, you are going to get the marks. Yes, Ravikant, it will be around 200 atm. Yes. So it will be heterogeneous catalyst. Fine. So that's where we have the catalyst. All of you have understood? Promoters and catalyst. All of you have understood? So that's where we have the reaction condition. And at the end, you can provide one statement that based on the, someone had told that Le-Chatler's principle. Yes, based on the Le-Chatler's principle, this condition has been designed. Based on the Le-Chatler's condition, this condition has been designed, especially high amount of pressure is applied, that is based on the Le-Chatler's principle. Because if you observe on left hand side, we have 3 plus 1, 4 molecules of gas. On the left hand side, we have 4 molecules of gas. And if you observe on the right hand side, we have only 2 molecules of gas. This one no need to write in the exam. Only thing is you should write based on the Le-Chatler's principle, high amount of pressure will be applied. That is fine. But to make you understand, I am explaining here. So 1 molecule of nitrogen gas, 3 molecules of hydrogen gas. That means 3 plus 1, it will be 4 molecules, right? And another molecules of ammonia gas. So therefore, when I am applying high amount of pressure, reaction will be forced to move toward the rightward direction. That's what the Le-Chatler's principle tells, right? So when you alter the condition, we can disturb the reaction equilibrium, where a reaction will attain a new equilibrium. So which is that new equilibrium? Where all the reactant will be converted into product. That will be the new equilibrium condition. How we have attained this new equilibrium? By applying very high amount of pressure. Since product side less amount of gaseous molecules are there, so therefore reaction will be shifted towards the rightward direction to compensate this high amount of pressure. So that's where it is based on the Le-Chatler's principle. All of you have understood? Fine. If it is asked for 4 marks, better to go with flow chart. This is fine, but better to go even with flow chart. Now whenever I am talking about Haber's process, first one, it will be always compression. That is because we have to apply huge amount of pressure, right? So therefore, always stage 1 or step 1 will be compression, where we are compressing the gaseous reactants. So that's where we have the compression. Next, step 2. Step 2, it will be conversion. Even you can use SS, conversion. So conversion of what? Conversion of reactants to product. Yes, sir, Chit. Increased in equilibrium. Yes. So where less molecules of gaseous molecules are there. Yes, you are right, Archit. So step 1, compression. Step 2, conversion. And step 3, cooling. Okay, fine. Why cooling is required? To convert gaseous ammonia into liquid form. Fine. So that's where we have the cooling. So what I mean to tell you is, when you are writing the flow chart or when you are designing the instrument, you should have 3 portions. One is compression, next one is conversion, and next one is cooling. Okay? So that's where we have the 3 stages in the Haber's process. Now, it may not be exactly as that of your NCERT, but we will try to copy whatever is there in your NCERT book. Okay? So now we have the nitro into a instrument or part of the instrument which is called as compressor, which is called as compressor, which will maintain around 20 megapascal, which will maintain around 20 megapascal of pressure. Now from there, anyway, molecules will come here, then it will go down. From there, it will go to catalytic converter. So it will go to catalytic converter. Catalytic converter, where we will be having iron oxide, then we will be having Al2O3 alumina or K2O. All of them will be there in this compartment. And the temperature they will maintain here is somewhere around 700 Kelvin. Right? So from here, whatever ammonia will be produced, from here, whatever ammonia will be produced, it will pass to coolant. It will pass to coolant. Right? So that's where we have the coolant. So what will be there here? It will be ammonia. Until here it will be nitrogen and hydrogen. But now once it is coming out of the catalytic converter, it will be ammonia. Right? So where ammonia will be collected, and if any leftover nitrogen or if any leftover nitrogen and hydrogen is there, once again it will be given back to, once again it will be given back to compressor and it will be recycled, so that to avoid the wastage, if by chance any nitrogen and hydrogen gas is left over, so I will write here, so leftover nitrogen and hydrogen, it will be passed once again to compressor, so that it can once again go through the catalytic converter, nitrogen and hydrogen during the process. Fine. So this is where we have the commercial preparation of ammonia. All of you have understood? So what is that another chemical property of nitrogen? When a nitrogen is heated with hydrogen, it is going to form the ammonia. So that's where we have modified the condition. We have altered the condition in such a way that we have made utilization of this property of nitrogen as commercial preparation of ammonia, which was first designed by Fritz Haber. Therefore, they call it as Haber's process. All of you have understood? Any doubt? So, first thing is reaction condition with balanced equation. So, from where ammonia comes out, sir? Ammonia will be collected here only. It will be in liquid form. Coolant means very, very low temperature. So, it will be in liquid form. So, later it will be drained out from here on. Fine? Because it is the liquid. But once it is exposed to room temperature, definitely it will be a gas. Fine? So, from here only it will be collected. Okay? Any other doubts? So, that's where we have the condition. Please remember, here ammonia will be in condensed form. That means liquid form. Okay? So, therefore, we are cooling the system. So, any other thing? Any other doubt? Fine, it's very, very important. Haber's process. So, reaction condition you should remember, and one sentence, that is, high amount of pressure will be applied to based on the Le-Chatelain's principle. That is fine. Okay? So, all of you have understood? Any doubt on Haber's process? So, shall we move to the next one? Okay. So, we will move to next one, that is, once again, I can tell not as very important, but I will mention it as important. That is, property of ammonia. That is with respect to property of ammonia. Now, ammonia is a very good Lewis base. That all of you will agree. Because even first year it was there in chemical equilibrium, right? So all of us we know that it is a Lewis base. But can anyone tell me what do you mean by Lewis base?
Electron by donator.
Okay, very good. Mayank has given the answer. Anyone else who is typing? So I will give 1 or 2 minutes. 1 minute. Because ammonia has a Lewis base, no doubt. Okay. So Lewis base means electron donors. Yes, yes, very good. So they are electron donors. Now, why ammonia should be an electron donor? That is because due to the presence of lone pair of electrons. So due to the presence of lone pair of electron, yes, that's why ammonia can behave as a Lewis base. Now under which condition? Where there will be a presence of electrophiles. In the presence of electrophiles, ammonia will behave as a Lewis base, where it will donate electrons, it will make a bond, and that's where NH4 plus ammonium it will be formed. So that's where ammonium ion will be there. Please remember, ammonium is a compound where we have covalent bond and coordinate covalent bond. Right? Ammonium is an example where we have the covalent bond and once again coordinate covalent bond. What is coordinate covalent bond? Where one of the element in a bond will be invest in the electron. Right? Another element will not be having any electron to invest. So that's where we have the coordinate covalent bond. A altered form of the covalent bond only. That's where we have the coordinate covalent bond. So ammonium is the example. So due to this reason, whenever ammonia is treated with water, that's what I am talking about, liquid ammonia. Liquid ammonia means where ammonia is in the form of liquid, but whatever ammonia solution it is there in your lab. So that's what, where ammonia is mixed with water. Now all of us we know that water is the molecule which can have equal amount of H plus OH minus. Normally water will be considered as a neutral species. Why it will be considered as a neutral species? Because it can provide equal amount of H plus and OH minus. Now same logic. So therefore it will be formed as ammonium hydroxide. Whatever H plus is there, it will become ammonium. Whatever OH minus is there, it will make the compound ammonium hydroxide. So that's what ammonia solution. And some amount of ammonia will be left over. So that's what, whenever you open that bottle, you will get pungent odor. Very strong odor will come. Anyone of you have tried smelling that ammonia bottle? Try it now. Means this time you can try it out, but don't take too much, don't inhale too much of that. Because ammonia is toxic to our body. It's very toxic, fine. But nothing will happen once you smell it. Some people, oh, Raghavendra sir told it's very toxic. So inhale, oh, I'm becoming unconscious. Nothing will happen like that. But if you inhale too many times, then it is toxic. Fine? So that smell is due to ammonia, which is coming out of that bottle, leftover ammonia. Fine? So this property shows that ammonia is a basic molecule. This property shows that Lewis base character of ammonia. Yes, Ravikant, you are absolutely right. Ammonia is a colorless, pungent odor containing gas. Yes, you are absolutely right. Fine, all of you have understood this one. So now, based on this concept where Lewis base character or basic character of ammonia solution, we have some of the reaction which justify this property. For example, I have zinc sulfate. I have the zinc sulfate, metal salt. I have the zinc sulfate. When this zinc sulfate is treated with, when this zinc sulfate is treated with ammonium hydroxide, that is ammonia solution. When it is treated with ammonium hydroxide, when you heat it, now you are going to get zinc hydroxide. You are going to get zinc hydroxide and ammonium sulfate. Okay, fine. So whatever I have written, whether they are correct? Any one of you? By mistake I wrote zinc OH twice. I would have not written that one. All of you will agree all the compounds are fine? No. The ammonium sulfate. Sulfate is -2 and ammonium is +1. So cross multiply. So it should become ammonium twice sulfate. Right? So that's where we have the zinc hydroxide and ammonium sulfate. And ammonium sulfate. So displacement reaction, it is nothing but a displacement reaction. Sulfate with zinc, it has moved to ammonium in the product. OH minus with ammonium, it has moved to zinc in the product. So that's where this zinc hydroxide, it will be precipitated. It will form the white precipitate. It will form the white precipitate. We have to balance. Okay, fine, it's easy. We have to write 2 molecules of ammonium hydroxide, equation is balanced. Fine. So that's where one property which shows the basic character of ammonia solution. That shows the basic character because it is converting metal sulfate to metal hydroxide. So that property is the basic nature of the basic solution. Fine. So now another example if you want to take ferric chloride, FeCl3. That is nothing but ferric, right? Ferric chloride. Because when I am telling FeCl2, that will be ferrous chloride. So I told ferric chloride, FeCl3, because iron will be +3 oxidation state. Once again, I treat with the ammonium hydroxide. Naturally, there will be formation of FeOH thrice, that is ferric hydroxide, that is nothing but ferric hydroxide plus another product will be ammonium chloride. Now this ferric hydroxide will not remain as it is. Immediately it will get converted into oxide, Fe2O3 with bound amount of water molecules. Ferric hydroxide immediately will get converted into ferric oxide. So I think in your textbook they have written directly this one. Actually, first product will be this one which will get converted into ferric oxide. Okay? So that's where we have the brown precipitate. This will be a brown precipitate. It will form a brown precipitate. So here I should make it as 3 and here also I should make it as 3. Now it is balanced. Okay? So another reaction which talks about basic character of ammonia solution. Another example for displacement reaction. Another example for displacement reaction. All of you have understood? Fine. So these are some of the reaction which justifies the basic character of ammonia solution. Which justifies the basic character of ammonia solution. All of you have understood? Fine. So in that case, we will move to another 2 important reactions. May not be very important at all, but okay, fine. We will keep it as a important reaction. That is reaction of ammonia. Reaction of ammonia with the metal ions. Here I have discussed about ammonia solution. That is ammonium hydroxide. Same way, For example, if I take copper sulfate will form a beautiful color solution, or copper sulfate will have a beautiful color. It will have sky blue crystals. It will be a sky blue crystals. Whenever it will be added to water, it will get dissociated as Cu plus 2 and SO4 minus 2. Right? So that's where they will be dissociated when added to the water. Copper sulfate as a crystal, when it is added to the water, it will get dissociated as copper plus 2 and SO4 minus 2. And whatever copper plus 2 is there, now it's going to react with the ammonia, and here it will be blue color. Okay, so that solution will be blue color. Now when it is treated with ammonia, it will form a coordination compound, which you are going to discuss in detail about coordination compound in coordination compound topic itself. But for time being, I will tell, this is another example for Lewis base character of ammonia. Yes, it is another example for Lewis base character of ammonia, where these lone pair of electron, it will try to make the coordinate bond with the Cu plus 2, because there is a deficiency of 2 electrons. Fine. So therefore Cu plus 2. So coordinate bond means one ammonia, another ammonia, another ammonia, another ammonia. That's where we have the coordination complex. That means leftover plus 2 charge will be there. Leftover plus 2 charge will be there. Fine. So that charge coming from copper ion. That charge is coming from copper ion. That's why plus 2 charge will be there, which can be in association with minus 2. If I have taken copper sulfate, only cupric ion, in your textbook I think they have given only cupric ion, then no requirement of writing sulfate. Okay, so that's where I have the 4 molecules of ammonia. I have the 4 molecules of ammonia. Now this particular compound can be called as tetraamine. And what is the charge on the copper? Plus 2, right? So 2 sulfate. Anyway, we are going to discuss about naming the compound in detail. It is also called as cuprammonium sulfate or tetraamine copper sulfate. That Stokes notation, this in bracket, that is related to oxidation state of the metal ion. Okay, that is related to oxidation state of the metal ion. Okay, that is with me only. Fine. That's where we have the tetraamine deep blue. That means much more dark blue color solution. Whatever light blue color is there, it will be converted into dark blue color. So this is how it is the confirmation for the presence of cupric ion. Is the confirmation for the presence of cupric ion. You might be having light blue color, but still you are not sure whether it is due to cupric ion. So if you add ammonia to that, then if it is getting converted into dark blue or deep blue color, then it is called as, okay, Ravikant. But here it looks fine. So for everyone it's like buffering. Okay, fine. Now it's correct. Fine. So that's where we have tetraamine copper sulfate, deep blue. What is the advantage of this reaction? So this reaction is helpful for the, okay, Shashank. Even now it is buffering. Okay, now we have reconnected. Whether it's fine?
Copper sulfate and water is called blue electron. Is copper sulfate and water called blue electron or in ammonia?
Which one?
Blue electron.
Okay, fine. All of you are understood? So that's where we have the deep blue color. And normally copper plus 2, always it will form the blue color solution, no doubt. It will form the blue color solution in the water. So that's why we have the reaction. What is the advantage? It is meant for identifying the presence of cupric acid. That is one thing. And another important point here is this reaction justifies the Lewis base character of. So video is correct, right, for all of you? Oh, fine. So in that case, this is one reaction where we are detecting the presence of cupric ion by adding the ammonia to that particular solution. So we'll come to next one. We have silver ion, and all of us we know silver will have the +1 charge. So this silver ion, whenever it is treated with Cl minus chloride, so naturally it will form silver chloride. I think you people have done this test in salt analysis, right? Chloride test, presence of chloride. This is one thing. Silver nitrate you are going to add, right? Which will form the white precipitate. Which will form the white precipitate due to the formation of silver chloride. So whatever aqueous silver ion and whatever aqueous chloride is there, it's going to form the silver chloride. Now, this silver chloride, once again, this silver chloride, which is actually a white precipitate, when it is exposed to ammonia, now it will become soluble and colorless. So that's where we have this silver, which can make coordinate bond with the two molecules of ammonia, and +1 charge will be there, which will be in balance with the Cl minus. Fine? This Cl minus. So therefore, it will become aqueous. It will become aqueous. Fine? So, and another important thing here is, it is a colorless. It is a colorless complex, coordination complex. Now, this molecule can be called as diamine silver. Diamine silver. 1, because +1 is the oxidation state of metal ion. So 1 chloride. Okay, na? So chloride. So that's where we have the name of the compound. Okay, that's where we have the name of the compound. So diamine silver chloride. Fine, which will form colorless molecule, soluble in water. So once again it confirms the presence of silver ion. So what will happen? Whenever if silver ion is there, when you are adding chloride, it will form a white precipitate. Now this white precipitate, when it is exposed to ammonia, immediately it will become colorless solution. A precipitate will get converted into solution. It will become solubilized because no more silver chloride is there now. Fine? So another important property of Lewis base character of ammonia. Another important reaction which justifies the Lewis base character of ammonia. Any doubts? So that's where here also we can use the ammonia for the detection of silver ion. For the detection of silver ion. Fine? Okay. Now we will move to the next one. That means oxides of nitrogen. We will move to the next one. That is of nitrogen. Ammonia is done. Now we are moving to the next one. That is oxides of nitrogen. Now, when it comes to oxides of nitrogen, now we can have nitrogen as N2O. Now it will be called as nitrous oxide. N2O, nitrous oxide. If I have NO, now it will be called as nitric oxide. It will be called as nitric oxide. Now if you observe nitrous oxide, where nitrogen is in attachment with each other and is also forming bonding with the oxygen. That is one form. It can have the resonance form, right? So where nitrogen can make triple bond, then it can be like this. So that's where we have the nitrous oxide, which can have in the resonance form, right? So nitrogen monoxide, nitric oxide or nitrogen monoxide, absolutely fine. Okay, but at the same time we have another one, NO2, nitrogen dioxide, NO2. So this is nitrogen monoxide, as someone had told. Even nitric oxide can be utilized. So this will be nitrogen dioxide. Now the question here is,
See which structure is more stable among these?
both resonance form.
Both
It's a resonance form. Now when it comes to nitrogen dioxide, that is NO2. Now this nitrogen dioxide, one in-text question or one question is that always it will dimerize to. Always it will dimerize to N2O4. Always it will dimerize to N2O4. What might be the reason? Nitrogen dioxide, always it will dimerize to N2O4. And I think any other N2O4. Anyone? That is because when I am talking about NO2, that means there is a partial double bond character. Fine. So there is a partial double bond character. Now problem here is this nitrogen will be with lone electron. This nitrogen will be with lone electron because it's going to invest 2 electrons here, 2 electrons here. So that oxygen will have the lone pairs of electrons. So therefore it will be having lone electron. So to avoid that lone electron, it will make the dimers. So that's where we have the dimer. That is N2O4. That is nothing but N2O4. So to get rid of this lone electron present on the nitrogen. Fine. So now another important point here is this one. Both the oxygen, between nitrogen and oxygen, they will have the partial double bond character due to the resonance feature. So in that case, why NO2 will be converted or dimerized to N2O4? To get rid of the lone electron present on the nitrogen. To get rid of, in the sense, due to the presence of lone electron on the nitrogen. Fine. So therefore they will be dimerized. Okay. All of you have understood, and try to recollect or try to write the oxidation state of this, in this molecule, oxidation state of nitrogen. Naturally, in all the cases it will be positive oxidation state, but what is that actual oxidation state? Try to write it down. Fine. So these are some of the oxides of nitrogen. Okay. So anyway, I will stop here. Any doubts? Any doubts? Okay. So anyway, I will stop here. So in the next class, we will continue with another important preparation, that is preparation of nitric acid. Okay? Fine. Thank you. Take care. Thank you.